a little bit of functional analysis. The idea is that we start from this polynomial interpolation, okay? And this will introduce us to the functional analog of what we discussed in class, which are the ideas of orthogonality, for example, idea of a null space and space spanned by a set of functions, right? And once we get there, then our objective is to get to the Fourier transform, okay? So the Fourier transform, you're going to see it during your coursework in many different sources, right? You're going to see it, let's say, for complex numbers, you're going to see it for vectors, you're going to see it for functions. But the way in which we approach it through this set of slides should be something compelling, okay? So the thing that you guys probably have never thought of, but but it's very natural for us to imagine, is that as you have a space which is induced by vectors, it is just as easy to induce a space of functions, okay? So for example, you take the space of polynomials, right? The space of smoothly twice differentiable functions. You can build the geometric concepts that are very familiar to you for vector spaces. You can just as well transport them to the space of functions. Okay, so now instead of having a space which is x, y, and z axis, then you have 3 polynomials, right? And concepts such as orthogonality, norm, inner product. They all translate very naturally to the space of functions. Okay. So the standard way to do that is to consider a one-dimensional interval. So we take this interval I between A and B, and if we fix ourselves over this interval, then we don't have to worry too much about integration, right? And so what we can do is that we can define a set of norms over the space of functions. Remember that norms have to have these 3 properties. They have to be positively defined. The all zero function must have norm 0. Okay, it used to be that the all zero norm has to have a norm 0. Now is that the all zero function must have norm 0. And then you have the triangular inequality, right? The norm of the sum of 2 functions must be greater than the sum of the norms of 2 functions. Of course, the first one that comes to the simplest one that comes to mind is the maximum norm. Okay, since we are in a finite interval, the maximum. The definition of the maximum is a little bit easier than if you were in an unbounded interval. We can have an L1 norm in which we do the integration. Okay, now the summation over the vector becomes the integration over the interval. So this is the interval of the absolute value. The L2 norm is very natural, right? We integrate the square of the function, and also we can have a weighting factor as well. Everything is good. And then you know that once you have a definition of the norm, you can always induce an inner product, okay? So if you have to define a space, right, you need a concept, let's say you need a concept of orthogonality. And usually what we do is that we say that we start with an inner product, and then from the inner product, we build the norm as the inner product of a function by itself is the norm. So here you see that if you put f equal to f, then you get f times f complex conjugate, which is equal to the Euclidean norm. You see that this inner product induces this L2 norm, but of course also the other way around works. And you can go from the norm to the inner product. There is a formula which is it's called like the rectangular formula. I always forget, guys. But basically, it's very intuitive. It's very geometrical. You can look it up. So as I was saying, so you can, if you want to define a space, you can either start from a norm or you can start from an inner product, whatever comes more natural to you. And usually what people do is that you consider infinite dimensional spaces, okay? Because now if we look for orthogonal functions, so functions that have an inner product equal to 0, then there are an infinite amount of functions that we can define like this. But usually people consider some sort of finite basis, right? So what we can do is that we can consider only, let's say, 1 to m type of basis function for the space, and then we say, well, we compute a space, right? And we say that the space is computed by this set of functions. So now something else that we can do is that we can define a certain set of discrete points for this function. Okay, so the function, as we said before, was defined on a continuous interval. What we can also do is that we can define to a discrete interval. Okay, so now we will call these nodes. Okay, and let's say that we have m+1 nodes, and the nodes go from 0 to m. And now when we define the norm, we don't define the norm with the integral. We just define the norm as the summation over the set of nodes that we have chosen. Okay. And now if we do this operation, then you see that we go from a function that is on the continuous space to a function over a discrete set of nodes. And this gives us, again, a beautiful vector. So this is how we bridge from functions to vector. And now we can define the discrete product, the discrete inner product, not for all the interval and consider the integration, but considering just the inner product over the support, right, over this set of nodes. Okay, so of course this is all very natural. You can imagine that the continuous version of the inner product will be the limit when the number of nodes goes to infinity, and you can in your mind come to grasp with how this summation will converge to the integral with the correct scaling of the area under the curve. Okay. So now we can think about a set of basis function of n basis function for the functional space that we have, and for example, we can ask ourselves how can we build a set of basis function using the polynomials, okay, or the monomials. And then what we would say is that if you give me a set of basis function for a space, what I can do is that I can build a finite dimensional approximation of a function over the set of bases that you give us. Okay, so here we're back at the continuous case. Let's say that we define this basis function to be phi k to the x to be x to the k. We discuss later whether this set of function is orthogonal or not. Whether the basis function is orthogonal or not, we can still say that we want to consider the approximation, the functional approximation problem, in which we are given a certain function, and we say that we build the function as a weighted combination, as a weighted linear sum of the elements in the basis function, and then we will set up a least square approximation. Okay, now we will be on the continuous space, in which we say that we want to find the set of coefficients C in the definition of our function in the space, in the functional space induced by this phi 0 to phi n basis. And what we want to do is that we want to minimize the error approximation, and this approximation error will be in a certain norm. And the norm that we take will be an L2 norm. Okay, and so this recovers the idea of the orthogonal projection. Okay, because remember that we said if somebody gives us a vector, okay, we want to project a vector from let's say a larger space to a certain subspace, let's say to a hyperplane. And when we do the projection of the hyperplane, what we do is that we look at the coefficients of the basis of the hyperplane, and we ask, okay, we choose this coefficient so as to minimize the projection, the error, and this corresponds to a projection. Okay, so now if we go back to the case in which we have a set of points in which we evaluate the function, then everything becomes a matrix product, a matrix problem. Why? Because now this y is evaluated on the point over this x interval. This basis function are also evaluated on this interval, and now we can play around with the dimension, right? So we have 1 to m nodes in which this function has to be specified. The basis function, we have n basis function evaluated in m points, right? So this is now a matrix, okay, an n times m matrix, and so this coefficient c, then there will be there will be a vector of size 1 over n, okay? So 1 over m nodes in the function, n over m basis function that we imagine in the matrix, and 1 over n is the weighting coefficient of the nth basis, okay, which is specified over m different points. Very good. So, sorry guys. So we get back to this problem in which we are solving a system of equation, and of course, depending on the choice of n and m, we can have an overdetermined or an underdetermined system. And if n is equal to m, then we have a nice, very straightforward square matrix that we know how to solve in many different ways. And the general way of solving all sorts of least square problem, as we saw, is to have this pseudo inverse here, right? So we will multiply by both sides by the transpose of this basis matrix, and then you see that this will induce this matrix. And the best way to have a matrix here which is well behaved is, of course, to have a set of orthonormal bases. What does it mean for the the basis to be orthonormal? It means that if we take the norm of a function, the norm is equal to 1, and the inner product between one of a function and any other function in the set of basis function, then we will have 0. For mathematical reasons, we like to call this a delta. Okay, so a delta function is a function which is equal to 1 in one point and 0 everywhere else. No, just remember the sound of my voice regarding this. You'll spend a lot of time talking about the delta function in your future. And so, if we ask this condition for the basis to be orthonormal, then what you will obtain is that the product phi transpose phi will be equal to an orthogonal matrix. And so when we want to solve this problem, we don't have to worry about inverting this square matrix in the pseudo inverse of the matrix. We just have the phi transpose, and then we are all happy because we just have to consider the evaluation of the function and the interval x, and then we will say that the coefficient of the function f x of k times phi I is equal to x of k. Okay, so this is all of a sudden this is very beautiful to us, right? Because all of a sudden the problem of determining these coefficients became simply to evaluate the function at the node index m, okay, and multiplying by the orthogonal basis. So this is all of a sudden we went through a set of calculations that all seemed reasonable, but now things are getting interesting. I know, and now we can talk about various ways of determining some interpolations. Okay, so what are the interpolations that we will want to consider? The first one that comes to mind will be a piecewise linear interpolation. So you interpolate the points with chunks of linear functions that they go from one point to the next. Okay, very good. So in this case, you will have that you have zero order continuity, right? So the function is continuous in the zero derivative, but if you go to the first derivative, then the function will be discontinuous with the first derivative. So you decide to do a little bit more effort in your interpolation, and what you do is that you impose, for example, second or third order derivative continuity here. So now if you interpolate with a higher degree polynomial among your points, among your nodes, what you can do is that you can impose that the 0, 1, 2, 3 order derivative, they are all continuous, right? So the function is continuous at the points of the nodes, then you can have a smoother function. And then, of course, you can figure out other interpolations which are meaningful to you, right? So, for example, in the spline interpolation, it's something which is very commonly used in computer graphics. And what you do is that you impose that the first and the second derivative at the node on the left-hand side, they coincide with the right-hand side, so that the function is continuous up to the second derivative at the nodes. Okay. So now we have found the problem which we are interested in now, which is the interpolation problem. Okay, because if we have to define a set of interpolating function phi of x, which passes through the data points xi, comma yi. Okay, so you have a certain input function which needs not to be a scalar. This could be a vector, but the function evaluates into a scalar. Okay. And remember that these xi functions, we call them the nodes. Okay. So the type of interpolation function that we are interested in have different qualities, right, that we wish to use in different contexts. So the first one that we like are polynomials, and we like polynomials because for example, the multiplication of polynomials and the sum of polynomials, they give rise to very simple expressions, okay? Because you specify a polynomial by its coefficients, and if you take the product of two polynomials, then the product polynomial will have coefficients, which is the convolution of the coefficients of the two starting polynomials, right? So very easy to calculate. So that's why we like polynomials. We like piecewise polynomials for similar computational reason. And later on, we're going to see Hermite interpolation and spline interpolation. Something else that we really like are trigonometric functions. The reason why we like trigonometric functions, it's because it is very easy to define the orthogonal space. Okay, so if you have the product of two trigonometric functions, you remember that you have those beautiful sum formulas, right? When you have the sin of x plus the multiplied by the cosine of x is equal to the sine, cosine, cosine, sine. You know, remember those formulas, and those formulas make it very easy to generate a set of orthogonal functions for trigonometric function of a certain frequency very, very easily. So this is a very crude simplification, but actually, let's say that a lot of operation in engineering, they rely on this. They heavily rely on projecting function on the trigonometric basis, because many reasons, but let's say also physics, right? There are many things that we understand about physics if we move to this trigonometric space. Okay, it's a much larger conversation that we should have some other time. And historically, there's been a lot of definition of orthogonal polynomials. So this Chebyshev polynomial, Legendre polynomial, a lot of mathematicians spend a lot of time in order to do the following, right? So polynomials, if you take them, let's say x to the k, as in the previous slide, they will not be orthogonal, of course. But what you can do is that you can find some ways of generating orthogonal polynomials with a lot of structure, so that when you have to build this interpolation, then things compute very easily. Okay, we're going to see some example later. Okay, so where is an interpolating polynomial? So as we said, let's say x to the I, it's a polynomial term, and if we look at the inner product between x to the I and x to the j, this is not these are not two orthogonal functions. Okay, so what do you want to do? What you want to do is the following. You want to define a set of basis function, this phi of x, and then you say, oh, this phi of x is going to be equal to a sum of ai times xi, and I want to generate multiple phi's, so that phi I and phi j are going to be orthogonal. Okay, so the coefficients a1 to am will be the solution of the linear square, so that I can say that my phi of xi is equal to aj times xi to the j, and then we can put this in a nice matrix form, as we did before. So we evaluate the basis function into the different nodes that we're trying to approximate, and then this will give rise to the van der Monde matrix V, in which xi of j is equal to x subscore I superscript j, right? And this ij is the evaluation of the jth power of the polynomial and the ith point and the ith node of my set. Okay? So then, if this is the property that we wish, then you can prove that if you have VA equal to x, then by induction you can prove the determinant of V is equal to the product of j less than k of xk minus xj. Okay, so let's say that you have these 3 points, you have these 3 nodes in which you're evaluating the function. Okay, in position Vij you have xi of j, and then you will have that the determinant will be x1 minus x2 times x2 minus x3, and this will be the case for m equal to 3. So then, if we choose the interpolation points to be all different from all unique, right? Then we will have the determinant of the function will be the determinant will not be 0, so the function will not have eigenvalues in 0. And of course, if you choose the xk's to be larger than the xj's, right? So you order the points so that they are in increasing order, then this will be positive semi-definite matrix, so all the eigenvalues are going to be positive. So we can reconduce the polynomial interpolation to solving a system of linear equation, but it's easy to see that the problem is ill-conditioned, right? Because let's say that we are doing computer graphics, right? And we want to specify a volume with a set of points and then have a smooth interpolation among these points. Then, of course, we will want to put a lot of points so that our interpolation is very smooth. We don't see any sharp edges. But of course, this will mean that the xk and the xj becomes smaller and smaller. And we see that we know that if we have eigenvalues which are very close to 0, then the determinant. We know that if the determinant gets very close to 0, it means that we have a bunch of eigenvalues close to 0, and so the system becomes ill-conditioned. Okay, so we see that this interpolation problem it corresponds to a solution of a system of equation, which is something that we have learned how to do in the past months, but it becomes ill-conditioned as the problem dimension increases, of course. Very good. So remember that when you see a polynomial, you have many different ways to write the polynomial. Okay, so in the left-hand side, we write the polynomial in terms of the coefficients, when on the right-hand side, we write the polynomial in terms of its roots. Okay, so here we see that we have a polynomial of order 2 that has coefficients 1, -2, and +4. And here we express the polynomial in the same, we express the same polynomial as the product of its root. And so, so if we are trying to do approximate a certain function, you can imagine that what you're trying to do is that you want to choose the polynomial basis, and then you're choosing the m basis, where m is equal to the number of nodes that you have, so that you have a square matrix, a square matrix in your polynomial approximation matrix that we saw before. And then if you use this multiple basis to represent your space, then it's easy to see that what you're doing is that you're trying to compute the projection of your function onto your basis, and then you will recover the matrix multiplication setting that we had a couple of slides ago. Okay, so now this motivates the fact that we have a function. We want to find its polynomial approximation. Okay. We have one route to do this, which is to solve this van der Monde matrix problem here and to solve the linear system of equation. This is ill-conditioned, so we don't like it too much. We saw what happens. And we have approach number 2, which is same problem, same polynomial approximation. But what we do is that we define a bunch of bases that we can choose the way we find reasonable from a mathematical perspective, for example. And then what do? We solve this projection problem, right? So basically, we evaluate the polynomials and we find the coefficients A that weights the polynomial, that weights the basis in order to produce the approximation Y. Okay, so now we are back to the problem of producing a set of orthogonal polynomials, and of course there are many ways of doing that. Remember that we have at most a degree m. So that helps us. And what we want to have is that this property that this polynomial is evaluated over this set of points x that we call nodes. And we're going to have an I and a j, right? So the I is the order, is the index of the polynomial in the basis, and the j is the index in the nodes. And we want the polynomial to be 1 when I is equal to j, and to be 0 everywhere else. Okay, so we imagine something that crosses the 0 point, the y equal to 0 at the various nodes, then it goes up to 1 and it goes down to 0 again. Okay. So this is what one will call a nodal polynomial. And the one way to show it, one way to consider it is this, right? So this is Wn plus 1 of x. So here you have your all nodes, and you have x minus xi. Okay. So basically, you take all your nodes, and you place a 0 in all of these nodes. Okay. So this polynomial here will go to 0 at all the nodes, because these are all zeros of the polynomials. Okay. Now it's clear what we want to do next, right? We want to remove one of these roots in any of these nodes, so that we can have this m basis function. And what we have to do is that we have to readjust the polynomial to have a value 1 in that point. So that's what we're going to do next. So if somebody asks us to give us the ith polynomial, the ith basis, this polynomial basis, we take all the roots, right? And we put a 0 in all of the roots. Sorry, let me say it again. We want to create the ith basis in our polynomial basis. So what we do is that we take the product of all the other nodes, and we put them as roots of this polynomial. And for our jth root, we have to go to 1. So here we put xi minus xj. So when we evaluate the polynomial in x equal to xj, here on top, we are going to have the product of xi minus xj for I different from j. We want to normalize this to 1, so we have to divide by xi minus xj. Okay? So a little bit of unfamiliar notation, but the logic is clear, right? So you have a polynomial with all of these zeros. You want to take out one of the zeros so that the polynomial will go to 1. And do you evaluate the polynomial, or divide the polynomial by the polynomial by the evaluation of the polynomial in xi, so that you normalize the value of the polynomial in xj to be equal to 1. Good. If you want to write this a little bit easier, you use this omega expression that you have here, product of all the zeros. And what you do is that you just say, oh, in order to remove the 0, just multiply by this, and then I normalize by this, by the evaluation of the polynomials here. Okay, so this will give you this Lagrange interpolation formula, and this is where you use this, right? So here you have the phi of x. This is your interpolation of the function yi phi I times x. So as we said, these are the two equivalent way of expressing the polynomial interpolation. And then what you do is that you put the value of the function here in the yi, and then you have the normalization factor at the bottom, and then here you have the product of all the xi minus xj. Okay, so you see that this computationally, this is beautiful, right? Because it is very simple. It is very easy for us to see where the zeros are, where the ones are, where the normalization is very, very clear. But as you can see, it's a little bit cumbersome, right? Because if you think of this in computational terms, as we have learned to do in the past few months, you see that you have a summation of a bunch of products. So this summation is over m, this is product over m. So you imagine that you have an m times m set of operations, and the operation inside, they are not summation, which we will tolerate, but they're multiplication. So it's really, really heavy on our stomach, right? We don't like this type of stuff. But of course, this was Lagrange. It was probably 1700s, so we did a lot of steps since then, and that helped us. So here is the classical example where you take a function, right? Oh, sorry, what happened there? Where you take a certain function, right? So you take a certain interval, this interval between 0 and 1, and you pick the nodes, right, to be 0, 1, 0, 2, 0, 3, blah, 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 blah. And then you can plot all the different Lagrange polynomials. So you see that you see the oscillation of the polynomial away from the 0, right? So you see that, for example, this is phi 1, right? So phi 1 goes down and then hits the 1, and then it hits all the other 0. Then you see the, what is it, the 5, 5, right? So this is gonna go 1 in 5. Yeah, this goes 1 in 5 here, right? And all the other points hits the 0. And right away you see what is undesirable about this set of polynomials, right? So there are a lot of large oscillations, right? Which of course do not violate what is the purpose of our interpolation problem, right? So because what we want to do is that we want to pin the function, right, in the y values that were given to us. Okay, so we want the interpolation to be correct in the y values. But what we haven't tested in the problem formulation is, for example, that the deviation of the function between two successive points to be smooth or to be linked, right? So since we're using polynomials, polynomials tend to grow very quickly, right? As the number of interpolation point increases. Okay, so x to the 5 grows fairly quickly as a function. Okay, and so it's clear that here we have 10 interpolation points. So these polynomials are all of the type, they all contain a term x to the 10. And so you see that the term x to the 10 allows this function to jump very widely in between the zeros of the functions. Okay. So of course, it's a little bit of a qualitative description, right? Because that x to the 10 grows quickly, everything is relative, right? But you understand what I'm trying to say, right? Basically, in our problem formulation, we haven't tested for these functions to be, let's say, smooth or well-behaved or to have limited variations. And here, we are very happy to hit with this function, the 1, right? In x is equal to 2. But you see that actually before we get to this one, the polynomial swing downward and then swings upward, so that when we hit the 1, we are actually past the peak that we have asked, and that's somewhat undesirable, right? So that it's undesirable that we want a function to hit a 1 and to hit 9 other zeros. In order to do this, the polynomial goes all the way to -6 and to +2, right? So you understand that these variations are not good from a mathematical perspective. Okay, very good. Then we proceed a little bit forward in time and we go to Newton, right? We move a couple of hundred years. So the idea is that the problem remains the same. We don't want to, we are still doing the interpolation using polynomials, but what we want to do is that we want to have a more mathematically stable ways of calculating our interpolation. And what we do is that we can choose a different set of bases that give us a different representation of the function. And we want to move away from this product of bases. Okay. So the idea that comes from Newton is to have a recursive formula to calculate the coefficients A in the basis. And we do the following. So we start with the polynomial d0i. Is di of 0 of f, which is equal, we ask it to this to be equal to f of xi, and the f of xi is equal to I. Okay. Then this formula is repeated, and we say that the di of k, so now the I is fixed and we're increasing the k, is equal to the di plus 1k minus 1 minus di of k minus 1 divided by xi plus 1 minus xi. And then you see that for all of these di's, right, the di's, they are all hitting the xi point. So we have m of this di of 0. Okay, so this index, what is it? Yeah, so we start from 0, then we put the 1 here, right? And when we put the 1 here, we have a bunch of d to the power of 0. So this one here, they're all available to us at the beginning of the iteration. Okay, so the iteration, sorry guys, where are we going? Other way, here. So these ki's, you understand how the recursion will go, right? So we start with the 0, then we'll calculate the 1, and here in order to calculate the 1, we need to set k is equal to 2, k is equal to 1, k equal to 1 brings us back to the d0 of I, and the d0 of I, we have them from d0 of 1 to d0 of m. So the formula makes sense, right? So there is no calculation that cannot be completed. That's what I was trying to say. And the first divided difference is this one here. And this is by applying this formula to the zero. That's what I was trying to describe before. And the first divided difference is equal to this beautiful formula here, right? Which is f of I plus 1 minus f of xi divided by I plus 1 minus xi. And this is the first order approximation of the derivative. Okay, so if somebody gives you 2 points of a function and asks you to approximate the derivative uses 2 points of the function, this will be the approximation of the derivative that you will give them back. Okay, and then if you go on to the d2 of I, this corresponds to the second order evaluation of the second derivative of the function, and so on and so forth, right? So these divided differences is actually sort of reconstructing the function based on its approximation, its derivatives. Okay, very good. So now we have another way of generating the coefficients, right? So here we have another way of generating this polynomial, okay? And we have this divided difference. It's all look good. We can implement it mathematically since everything's working fine. But we lost track of the goal that we had initially, which was to evaluate the polynomial interpolation. So now we go back to the problem, which is that somebody gives us a function f of x. We are trying to approximate it into an interval x of 0 to x of m using a polynomial interpolant. And something that we can do is that we can use the Taylor series to look at the error in approximating f of x with the polynomial phi of x. And we call this the error of approximation of the polynomial of order m. So this is em of x. Notice that our x are still continuous here, okay? And if we do this extraction, we know the polynomial interpolation will have this expression using the basis function. And then we know that the error in the Taylor expansion of the term m will be dependent on the f of m plus 1 derivative. So the error that we commit as this approximation error. Okay, so the polynomial interpolation remains the same however you decide to choose this interpolation polynomial, and the error scaling will always be of this order. The error scaling will be the order of the derivative there. And here we have the product of the nodes over which the interpolation was fixed. Okay, so yeah, so I think it's clear, right? So we have the number of interpolation points that we have, and this is the magnitude of the total error that we do. And then of course we want to look at the norm of this error. So this error is interpolated over all the exposition. In general, the L2 error will not be very good for us because the L2 error will not tell us what is the largest variation from the original function to its approximation. So we prefer to take the infinite error. So what we want to do is that we want to take the max of xi of f of x, and we want to show that this error, for example, goes to 0 as m goes to infinity. So now we have to choose how we put the points in the interpolation polynomial in order to send this to 0. We have no specific, let's say, when we choose the interpolation, right, we would like to have the interpolation method to be fixed for all of the functions that are given to us, okay? So we don't want to redesign the interpolation function for all different functions that are given to us. So the best choice that we have is sort of a uniform choice in which we put the points to be equispaced on the x-axis. So now somebody gives us a function. We have a set of orthogonal polynomials that have nodes equally spaced between 0 and 1. And then we go in, we evaluate the function, and we see what is the error. And the error that comes to us is this formula here, right? So what we notice is as follows, right? So the formula goes to 0 as n plus 1, okay? H to the n plus 1. And then on the bottom, we have 4n plus 1. And this is f of, sorry, this is an m, okay? This is h of n plus 1. This is only m's, there are no n's here. Because we choose n is equal to m in this case. And so here we have that this depends on the infinity norm of the m plus 1 derivative of the function, okay? So if the function has very smooth high-order derivatives, then we can have a very nice approximation of the function, okay? So this is something that was not, let's say, it's expected to us, right? it doesn't come as a complete surprise to us. And it's saying that if you're interpolating things with a polynomial, then the interpolation error is related to the derivative of the function, okay? And the way in which we understand this relationship to go is because we use the Taylor expansion in order to measure the error between the Taylor approximation and the polynomial interpolation. And so it's clear that this bound holds in this sense, okay? It's clear that we could have used, we could get a better, it's clear that we could obtain a different bound, but the tool that we use to obtain this bound is the Taylor approximation. So the Taylor approximation converts errors into derivatives. So this is the bound that we obtain with this bounding strategy. So remember, this is an upper bound, okay? So this is an upper bound. Or things are, we don't know how tight this upper bound is, right? And so here comes the counterexample, okay? So take f of x equal to 1 plus x squared minus 1, okay? So you see that when you take the derivative here, this polynomial increases, right? And so the function, now what is the function? The function is the blue one, right? So which is very smooth. And then you are taking these interpolation points, right? And you see that this is the polynomial interpolation, okay, across these 10 points. Okay, so the function is here, the approximation interval is -5 to +5. And you see that we have a dot at every, we have a node at every integer, included integer 1. The blue is the function 1 over x squared minus 1. And you're doing this polynomial interpolation. And you see the polynomial interpolation has a very large error, right? Has a very large error in this area. Okay, so not very nice. Very good. So remember that this is a bound, and yeah, you can. Yeah, so it's many things are hidden in there. Okay. Okay. So next is we can discuss the nodes, how to choose the interpolation nodes. So we said that in general, what we want to do is that we want to have an interpolation algorithm. Somebody comes to us with a function, and we just apply this interpolation algorithm. And so it is very convenient for us to choose uniformly spaced points. But of course, if we were given the choice to choose the interpolation points, then we will be able to do a better job. And of course, this will come at increased complexity. So the interpolation polynomials, as the degree goes higher, they tend to have oscillatory behavior and have very high peaks. And this is especially true if we move away from 0, okay? So you understand that a polynomial has small values around 0 because all the polynomials, they have to shrink down to 0. So as you grow up far away from 0, then the oscillatory behavior becomes large. Of course, what you can do is that you can change the centering of the polynomial, right? You can have a polynomial x minus alpha to the power of k, and this will move the center of the polynomial to alpha. But still, if you move away from, let's say, the centering of the polynomial, then you will have very large oscillatory behavior. But also the interpolation is unstable under small perturbations, okay? Because the polynomials, let's say they react very quickly. They grow very fast. They have this oscillatory behavior that emerge very rapidly. Let's say that somebody gives you a function, right? But the evaluation points, they are subject by an error, okay? So let's say that we are trying to interpolate some planetary motion, okay? And we have some observations from some telescope, and we want to trace some trajectory, some orbit, right? And so we use a polynomial approximation because we know that this does a good job, but our observations are corrupted by noise, right? Then if this noise enters in the system, this will cause an oscillation, right, in the polynomial, which is again related to the 2 to the power of n minus 1 times the infinity norm of the error. And so you see that this exponential growth of the error is very problematic, right? Because it's telling us that the best bound that we have tells us that there is an exponential amplification of the interpolation error. So what we can do is that we can use some specially chosen polynomial, and we can interpolate the derivatives as we do the Hermite polynomial. But yeah, but in general, the conclusion is that using polynomials of high degree is a bad idea. Okay, so this is sort of the lesson that we have. So what we would rather do is to have instead of one single polynomial that tries to cover all the interval, what we can do is that we can take our nodes, right, and simply have a different polynomial for all the nodes. Very nice. Very nice. Because now, in a sense, we are, instead of increasing the complexity, let's say in the order of, in the degree of the polynomial, we increase the complexity by adding more intervals of interpolation and keeping the polynomial order in each of the interval very low. Okay, so now this brings us to this piecewise Lagrangian interpolants. Very nice. The idea is that we use different low degree polynomials in each of the intervals, and we set the intervals to be in between the nodes of our interpolation. First thing that we can do is just piecewise constant, right? So we can just say that we evaluate the, we match the whatever. You understand what is happening here, right? So here I fix the value of the function to be a simple constant, and this constant takes the same value not for all the interval. So in this case, for example, I can fix that my constant is equal to the left edge of the interval. So this is a stairway function, and the step of the function of my polynomial y on the left hand side. Okay, this is a very crude approximation, piecewise constant. Of course, it's not particularly useful, but you can imagine that it's very stable. Okay, and it's very low complexity. So trade-off between complexity and memory, for example. Or you can have a piecewise linear. This is the one that we were describing before. This is the one where you choose a linear function in between the 2 points. And since now we have 2 coefficients, right? We have the 0-order polynomial and the 1-order polynomial coefficient. What we can do is that we can fix this linear interpolation to be the line that passes through the 2 points. And then using, again, our infinity norm, we know that we can bound the error between any 2 points, and now you see that the error bound is much nicer, right? Because you have h square, so h is the distance between 2 points divided by 8 multiplied by the infinity norm of the function, right? So we're really pushing down the error with an h square. Now our eyes don't see derivatives very well past the second derivative, I would say, but it's clear that if we have a piecewise linear interpolation, the first derivative is discontinuous. So what we can do is that we can spend another degree of the polynomial in order to smooth out the first derivative, and this will give us a piecewise qubit Hermite polynomial, right? And what we do is the following: we set the polynomial to have the value of the function there, and then we can look at the derivative and say that this derivative is a zi, right? And then when we fix the next polynomial, we ask the derivative on the left-hand side of the polynomial will also be zi, okay? So that we're introducing continuity in the derivative of the interpolation between the left of the node and the right of the node. And this is called the piecewise qubit Hermite interpolator. Okay. So notice that here you see here. Let me give you here. So you see here that we don't set the. Sorry. So here we don't set the derivative to be the derivative of the function. Okay. And this is because these piecewise cubic polynomials, they are more like smoothing polynomials, let's say. So you do not know what is the underlying true function, but somebody gives you a set of points and you want a smooth interpolation through the points. Of course, there is also a version of the polynomials in which you actually know what is the underlying function, and the underlying function tells you what is the derivative you should have. And so you pin this derivative to be the derivative of the true function. If you do not know what is the true function, but you just know the points, then you just want it to be smooth, okay? Again, so for this type of polynomials, I think for this type of interpolants, computer graphic, it's usually the application that one thinks about, right? So imagine that you receive a LiDAR scan of an image of a 3D object, then you cannot you don't know what is the true value of the surface in all the points, right? You just want to have a smooth interpolation. So in the case, it makes sense that you do not pin the derivative to some predefined value, but you just ask that from the left to the right of the interpolant we have the same derivative. Okay. Of course, in some other instance, you know what is the underlying function. You can set differently. Okay, very good. Now we get to splines. So this is we said that in the Hermite interpolation we fixed the first derivative. So the interpolation polynomial was C1 smooth, right? So it was smooth up to the first derivative. But we can also have a strong assumption. We can go to cubic splines. And if we go to cubic splines, what we can do is that we can ask for the first and the second derivative to be continuous in the left-hand side and the right-hand side of the node, okay? So we can ask that the first interpolating polynomial has the same derivative of the second interpolating polynomial, and also the second derivative is the same between the left and the right of the node. So now we are constraining, if you do this, we need more coefficients in our polynomial so that we have a system of equations to solve which has a larger set of equations and a larger set of unknowns. Otherwise, we cannot hope to match all the unknowns and all the equations. So if we do this, right, we have 2m minus 1 equation for the second derivative, 2m minus 1 equation for the first derivative. So we have a total of 4m minus 2 conditions. In order to fix this, then we will need a polynomial that is at least k is equal to 3, so that then we have everything works out. And it depends how you want to fix the edges. So the edges are where you have to decide which behavior you have based on the condition that you have. Often, right, if you're using these splines to solve some sort of boundary problem, let's say, maybe you want that the derivative on the left-hand side is equal to the derivative on the right-hand side, the derivative on the left edge to be equal to the derivative on the right edge, or you can just set the derivative to 0 so that they equal to 0. But basically, when you set up your system of equation, you're left with a couple of degrees of freedom left, which describe the first and second derivative of the first at the leftmost point of your interpolation, the rightmost interpolation point, and so you can just decide how to fix those equations. Not a big deal. And the nice property of the splines is that they have a minimum curvature property, right? So if you look at the curvature of the function, right, square, right? So if you look at the square of the second derivative of the function, this is in the interval. This is less or equal than that of the spline, and the error, right, of the spline approximation converges to 0 with these nice properties, right? So you see that the first and second derivative, they all go down with h to the 4, h to the 2, h to the second, right? So you're matching all the derivatives, so everything is nice and easy. And of course, when you go to Python, MATLAB, whatever, there is a lot of polyfit that you can do. This is the polynomial fit. When you call a polynomial fit, the function, of course, does a lot of things. And yeah, of course, this also extends to 2 dimension. Everything goes nice. And then you can have a 2D degree, right? Which is very used in computer vision, as we said. And when you do 2D, then you can have separable basis. Oh, we will do this later, okay? I will do this later, okay? We'll take a little bit of time. So I just want to do this. I just want to show you where does the spline come from, because we forget we forget the history of splines. Then we take a little bit of a break, right? Spline. See if I can find it. Here, this is it, okay? Here, I'll just show you. Let's see if there is, just a second, how to use. Let's see if we can find a nice YouTube video of this. Videos. Spline, how to use. Oh, wait. Just a second, guys. I thought I would be. Thought it would be faster for me. It's all about AutoCAD. We forgot the origin of this. Let's see if I can find it. If I do look at this, I see the table. No, guys, just 1 second, guys. There was a nice image that I found. Okay, this is the best image that we have. I'm not happy, guys. I'll try to find some better. So the splines, they come from boating, okay? The people that build boat, right? They needed to have reproducible ways of representing curves. Okay, so you're building a boat, right? You want to sell the drawing. You want to send the drawing of a boat to a guy who's on the other side of the world because he has to give you the wood with the right dimension to do it, right? So how can you communicate? How can you communicate a curvature? And it's let's say again it's the 1800s. Okay, today the topic is 1800s, right? So you're in the 1800s. How do you communicate the curvature to a guy, right? So what people have, they have these weights, right? And what they will do is they will describe the position of the weights, and then they will take some balsa wood. Some balsa wood is this very nice flexible wood, and or maybe also some metallic wire, some spring steel wire. So you know that if you can reproduce the position of the weights that the designer used, and you are on the other side of the world cutting wood, right? Then if you use the same position, then you're going to be able to obtain the same curvature. Okay. So look at this, right? So this is how people used to use the splines. Okay. So you're designing a boat. You have to draw a nice curvilinear line, but you want to do it in a way which is reproducible and also other people can be communicated also to other people. And so you will use this mechanical drawing tools. So this is balsa wood. I don't know how many guys have used balsa wood, but basically, if you're doing furniture design or model design, something like that, you will know this very flexible tropical wood, which is called balsa. Yeah, and you see how cool it is. Okay. So when people talk about splines now, they completely forgot what is the origin of this. And yeah, it's very cool. Yeah, you see here. Yeah, you will describe to people where the weights were. Right? They will recreate the curve that you had in mind. Okay, let's take a small break, guys. And let me ask you in chat. How much longer do you want to go? 1 hour, 30 minutes, 15 minutes. Okay, answer in chat, please. And let's go walk around and let's get some more. And I'll see you back in 2 minutes. Okay, 27. I'll see you back at 27. Hello, guys. So, how long do you want to go, guys? Tell me in chat, please. I'm happy to go however long you guys want. Now, Fal, how long should I go? Not even my own student tells me.
You look tired today.
Huh?
You look tired today.
30 minutes? Okay, guys, good. Because I don't know what goes on in your life, right? So I hope this is interesting, right? But if it's, yeah. You understand my point, right? I want you guys to have a good memory of your time with me. I don't want to bother you. 30 minutes, okay, good. I'm gonna go 30 more minutes. Good, so I hope I amused you with the idea of a spline. Good, then we were discussing, so the extension to the 2D case, right? Of course, you understand that x does not need to be a scalar, it can be a vector, the y needs to be a scalar. So what you want to know is that you want to repeat this on a certain R of n, right? So why go to 2-dimension when you can go to any n dimension? In this case, things get more complicated in the sense that we need to define a certain area in which the interpolation, in which the polynomial will have to live. And usually the easiest thing for us is to take rectangular polynomials, rectangular areas, sorry, because of course taking other tessellations will be more complicated for us, right? So you can imagine that on 2-dimension you can have some, for example, octagonal tessellation, right? But if you take any other tessellation, then you have to decide how the boundaries interface, and it's not as easy. So let's just do things easily, and we take a regular grid. And if we take a regular grid, then we have the beauty that we can take separable functions, okay? So let's say that we have our x, which is scalar x, scalar y, not the best notation, right? Let's say x1, x2. But we can say that the basis function on the 2-dimensional x, right, on the x1, x2, is equal to the product of a orthogonal function on the dimension x and an orthogonal function on the dimension j. Very nice. Also very natural, right? Nothing particularly scary. And so now we have the same polynomial interpolation, right? We can move it to the 2-dimensional case, right? We can say that if we have summation over I of j of f of ij, so these are the ij point in your 2D space. This will be a basis function fij, okay? And this is the product of the phi I and the phi j. So you use the same interpolation function, but on the 2-dimension. And here we still again see this Runge phenomenon, right? So we have this nice function, right, which is nice and smooth, which is our usual 1 over x squared stuff. And you see that the error jumps up at the edges of the interpolation interval. And this, as we said, this is something that we see often, simply because our polynomial interpolation are very oscillatory toward the edge of the interval. I'm worried about specifying, like using the correct language when I describe this. So remember that it's a qualitative statement. It's not a quantitative statement, okay? So, so we can also go a piecewise interpolation function. So we can take an interpolation that holds on the square. And what we can have here is an interpolation polynomial, which is bilinear, right? So we have the product of the x polynomial and the product of the y polynomial. The x polynomial, we pick it to be linear. The y polynomial, we also pick it to be linear. So now we have the product of the two polynomial contains the product terms x times y, x, y, and then the constant, okay? Then we have a coefficient for the, let's say, for the 1, 1, for the power 1, x power 1, y. Then we have a coefficient for the power 0, x power 1, y. A coefficient for the power 0, y power 1, x. And a coefficient for the power 0, x and power 0, y. Okay, so we have 4 unknown coefficients. And now we have to choose how to place these coefficients. And what we can do, of course, is that we can ask for this coefficient to equate to the interpolation points at the 4 corners of the rectangle. So this is what you call a bilinear function. Okay, so it's a product of two linear functions. Okay, very good. So it is better to think in terms of the in terms of the interpolating of the basis function phi j, right? So each of the basis function is a piecewise bilinear function, and we have the nodes now are in a grid. So the grid will be the point I comma j, and again, we just instead of looking at the whole space, we just look at the unit reference rectangle. So 0, 1, 0, 1 in the L2 square. And then every other function we would, let's say, we try to squeeze it down, like to compress it down to this square by compressing the x and y dimension, scaling the x and y dimension, and then shifting with a bias. Okay, so we can say that if we have the basis function for the 0, 1, 0, 1 square, then we will first let's say normalize, right? Let's use this machine learning term, right? We will normalize to 0, 1 square the data, and then we will put on the basis function. Okay, so that interpolation can only be on this object. So now let's start with the 0, 0 corner, and let's pick the basis phi hat 0, 0, and in this case this will become 1 minus x hat and 1 minus y hat. And this corresponds to a bilinear term. And if you plot this bilinear term, it looks like it's a hyperplane in 2 dimensions, right? So it's called a tent function. Okay, that's because it looks like a tent, guys. Okay, it looks like a tent. It's a straight up tent. And of course, this is not very smooth because the edges they are kind of rough. So if you want additional smoothness, then you will have a bicubic Hermite interpolation, which is the product of the Hermite polynomials in dimension x and y. And then you can also generalize trilinear interpolation. Okay, so if you want to go to 3 dimension, then you will have all these terms here: x, y, z, x, y, x, z, y, z, x, y, z, and then the 0 term. And this gives you 8 coefficients. And in this case, we're interpolating a function in 3D, right? A function over a space R3. So this corresponds to a cube in 3 dimensions. A cube in 3 dimensions has 8 vertices. So we will choose the 8 coefficients to match the 8 values of the interpolator of the nodes in the 4 dimension. Okay, so this is your 10 function. Okay, and this is the bilinear function. Right? Okay, on this. So you see that this is a 10 function, right? So you see that this is on the 5x5 grid. This is the bilinear function there. And then if you go to bicubic, then you have something smoother. So now you get this very cute d-impulse in the function. So as we said, this was for the rectangular mesh. So the rectangular mesh things are nice, but some people sometimes, again, this is very much a 3D graphic, right? Type of space. You can also mesh with disjoint triangles, or you can use a tetrahedral mesh, right? And then in the case, you can no longer use separable basis functions, right? Because now the basis that now you don't have this independence of the 2 directions. So the 2 dimensions are they're together. But what you can do is that you can still design interpolation for the reference triangle. And now for the reference triangle, you can choose a little bit what you're trying to interpolate, right? So for example, you could try to have a triangle around a node point, or you could put the node points at the edge, or you can try to be even more efficient and add, in this case, for example, 6 interpolation points with a triangle, right? So here now, when we do the matching of the basis function, right, you do understand that also we are pinning across triangle. We're also pinning the middle point of this triangle here, right? So this is very powerful, right? Because it adds smoothness between the interpolation of one patch and the other patch. Okay. So here there is just how the interpolation will go with piecewise linear over this triangular tessellation. Okay. So you see that these are triangles, right? So for each triangle you will have a constant value. Or here for each triangle, you will have a tanh function. Of course, many numerical ways of doing this. Using regular grids. This is what happens in MATLAB, right? So here you choose again this saddle function, and you ask for interpolation, and you see here, you see that the interpolation is nice and cute. And of course, if you move to a quadratic interpolation, you obtain something like this. I think it's very regular. So just a conclusion for today is like this. So we have known samples, and we want to interpolate with a set of interior boundaries, right? So we can do this with a basis set and a basis set of interpolating functions that we can use. So even if we fix ourselves to take a polynomial interpolation, it is usually better for us to formulate this as a set of orthogonal functions, so we can obtain the coefficients of the polynomial interpolation with a projection operation. Usually we are happy to use low degree interpolation. As we go to higher degree, then they become numerically more stable. If we want to do a better job, instead of increasing the degree of the polynomial, we're better off having piecewise interpolation. So we divide the interval in multiple intervals, and we create an interpolation for each of the interval. And then this also very naturally generalizes to the 2D dimension and to higher dimension. And yeah, I think we are going to do this. Okay, so now we move to this orthogonal polynomials. We thank the people at NYU for the nice slides. So the review this is what we just saw, right? So the Lagrange polynomial, the Runge phenomenon that says that the interpolation accuracy decreases as we move away from the zero. This comes from this oscillatory behavior of the polynomial. So we said that this is a least square approximation problem. You have a set of n bases and m nodes, and you're trying to approximate the m nodes with n bases. Blah blah blah. We just saw this, right? So this is what we just saw. So we said that we can also define a weight function. Okay, when we have this norm, and for different choices of the weight omega k, one then explicitly construct a basis polynomial. Okay, where the phi k is a polynomial of decay using a triangular basis. Okay, so here we have this inner product. We added the weight function, and then we said that this must be equal to the phi I times phi j. Okay, so if we put this to be the phi j, here we get this delta function. Remember, delta function is the function that gives you 1 if the I is equal to j and 0 otherwise. And now we have that here. We have the norm of the phi x square. So the idea is that if we repeat this, so this is how we choose the weight, right? We choose the weight to be the phi x square. So if you use equal weighting and you repeat this, then you obtain the Lagrange polynomial. And sorry, the Legendre polynomial. Got them French people, they pronounce half of the letters in the name. So the phi 0 will be equal to 1, the phi 1 will be equal to the x, the phi 2 will be equal to this object, and so on and so forth. And this is a set of sorry, notice that we have an expression for the end polynomial, right? So you have a recursive expression, which is this one here, and you also have expression for the end polynomial as a function of that. Okay, so this is the phi k polynomial as a function of the phi k minus 1 and the phi k. So it's sort of, you take the previous two polynomial to compute the current one, and also you have an expression in terms of n, the recursion step that you have. This should be a should be an n, not an k. This should be a k, not an n. And these polynomials are orthogonal in the space -1, 1. And if you take the product, then you see that the weighting coefficient that they have is 2 divided to I plus 1. Okay. So what we do is that we look at the interpolation polynomial phi of x as a function f of x over a set of nodes which are the x0 to xm. And then this gives us this orthogonal basis description. Okay, so now we have them as these objects. If we have given the orthogonality of this one here, if we take the product of the phi k with the phi with phi j, what we're extracting is a delta function multiplied by the aj, which is this coefficient here. So this is the norm of the aj function times aj, and this is equivalent to normal equation, right? So it's like saying that if we take the phi transpose times phi and we look at the ij term, then we will get the delta function phi ij, and this is what we were expecting. Okay, now let's do the Gaussian integration. So we just said that from the pseudo inverse equation, right, we get that the aj is equal to this expression. So the aj is equal to the normal of the phi j minus 1 times the inner product phi and phi j. So now let's say that we want to compute this inner product, right? So this is the integral over our interval AB of the weight function omega x. Remember that we allowed for the weight there. And then we have the product of the two function. And this one here are two polynomials, right? So now we're taking the product of two polynomials of degree m. So this says that the most degree m plus m minus 1, m degree 2m. And so the degree is at the most 2m, okay? So let's say if we can easily compute this integral, okay? So let's consider the polynomial of degree at most m, and let's ask ourselves what is the integral of the omega x times pm to the x dx. So we have the Lagrange basis, not the Legendre, now the Lagrange. See how confusing it is. And let's say that we have this psi 0 all the way to psi m, and they are a delta function, right? So if we put the phi I into the xj, we're gonna get a delta ij, okay? Because this function has it's a discrete delta function over this m support points. So okay, so any polynomial of degree pm. Any polynomial 2m of x of at most m can be easily expressed in the Lagrange basis like this. So you multiply the basis by the evaluation of the polynomial in the point xi. So now we put in this decomposition inside this integral, and since the integral is over a finite interval, and polynomials are integrable, square integrable. Then what we can do is that we can flip the integration and the summation. So here, the summation over m comes out of the integral. The xi is a scalar, and it's over the summation m, so it also comes out of the integration. And what we are left here is with the omega of x, phi I of x dx. And so this one here, we said that it picks, it picks the point here, right? It has the value of the point. So it picks this phi of x multiplied there. This is the polynomial, right? Using this formula there. So we get that the weights here, which are these omega y weights, are the integral of a on b of omega x phi I x dx. Okay, so this is now we have converted the weight function into a discrete set of points. So now we have that we can go back to the interpolation that we had before. So now for any polynomial p2m of x, then there exists a polynomial quotient qm minus 1 and the remainder polynomial rrm such that p of 2m of x is equal to this polynomial phi m plus 1 multiply the qm minus 1 times rm of x, and right, this integration here, right? So this is the integration we were trying to do before, right? This is the 2m integration we were doing before. No, going the wrong direction. This is the integration we were trying to do before. This one here, okay? This integration here. Now we know that we can write it as a quotient polynomial and a quotient polynomial multiplied by an m plus 1 plus a remainder polynomial of degree m. We write that there, and we type that this is the inner product of the phi m plus 1, qm minus 1, and the integral of the omega x times the rm. And now the phi m plus 1 are orthogonal, so when you put degree of degree at the most m, we have the phi m plus 1 qm minus 1 is equal to 0. And so we get that the integral of the omega x times p2mx is equal to the summation of the weights multiplied by the remainder polynomial. Okay, so we need to choose the nodes in which we want to do this, and if we choose the nodes to be the zeros of the polynomial f of m plus 1, then we are evaluating this remainder, right, at these points that are the 0 phi of m, right? So this term goes to 0. So we're just left with this. And then the final result that we have is that this integration is equal to the omega I by 2m xi. Okay, so a little bit of a mathematical ramble there, because we sort of lost track of what we were doing through the mathematical derivation. But this is a quick way of projecting a polynomial of degree m onto the orthogonal basis of the polynomial. Okay, so the integral that we were doing was a projection, and we did the projection in order to find the coefficients. So it turns out that the projection of the polynomial over the basis is equal to this omega I multiplied by the polynomial evaluated in xi, and the basis and the j basis evaluated in xi. Okay, very good. And the omega I, you see that we found them before. Okay, so the omega I, we found them before. So going back, right, we want to compute this. We want to compute this aj from the, and we were looking for the coefficients for the Legendre polynomial, which were the phi, not the psi. And the Legendre polynomial has this nice expression for their norm square. And so now we know how to compute fast the multiplication of the polynomial basis times for the polynomial of the interpolator with the polynomial basis j, which is equal to this, which tells us the expression for the aj. And basically the choice, the thing that we are doing here is as follows, right? So the value of the function is here, f of xi. The phi j we know because we can generate it quickly, right? This is a constant we can generate, but the beautiful thing is here is this omega y, which is the coefficient that we need in order to get this projection, this coefficient aj. This can be pre-computed because it depends only on the basis function, does not depend on the approximating function f, and so this gives us a fast way in order to calculate the projection, and this gives rise to the Gauss-Legendre polynomial. Okay, so this is the story. So for any within function of the polynomial phi k, which has k simple 0, simple in the sense that they do not repeat, in the interval -1 + 1, they're called the k-order Gauss-Legendre nodes, and which is the nodes in which this Legendre polynomial is a 0. Then the interpolating polynomial phi of xi is equal to phi of xi is equal on the Gauss nodes, right? So the Gauss nodes are the one in which the Legendre polynomial is a 0. It's called the GL, the phi GL of x. And through the orthogonality relationship, you can express this as a sum instead of an integral. So we are skipping the integral over. And so the inner product between the phi and the phi j is equal to the delta phi I square. And so we have a weighted discrete dot product that says that the inner product function f and the function g is equal to the summation of the omega i's fi times gi. Okay, so the fi is the function evaluated at the point I. Very good. Okay. moving on from here. So let's see if we can, yeah, we do a little bit. We finish this set of slides. So this one here, yeah, when you see this one here, it will make sense to you when you, yeah, it makes sense to you why you want to add a weighted function soon. Okay, so the orthogonal polynomial basis is discretely orthogonal if the dot product, right, is equal to this delta ij phi I times phi I. Okay, so we're taking the function by itself, we're taking the product, then we get a discrete delta ij. So this means that the matrix in the normal equation is diagonal, right? So that if you take phi transpose times phi is equal to the diagonal, and we have the norm of the polynomial here, and then we have that this ai coefficient in the interpolation are the evaluation of the function in the point multiplied by this object here. And so when we want to calculate the Gas-Legendre interpolation, it's very easy to compute. And we have that this interpolation, which is a polynomial in X, right, is the function evaluated at the endpoints multiplied by this sort of normalization factor that gives you the AI, and this is the Gauss polynomial. Good. Chebyshev interpolation. So there are other families of orthogonal polynomials that are also very useful. So there are a bunch of them, right? So when we say useful, usually means that the n approximation has a closed form expression in form of n, right? Or that the recursion for obtaining the interpolating polynomial is very convenient, one of these things. Another famous one is the Chebyshev polynomial. And you choose the weight function omega of x. And now we said that if we choose the weighted function and we put it in the norm, then this is going to generate the polynomial for us. Okay? And these are generated recursively as follow. So you see that the recursion is easier than the Gaussian polynomial. And then the orthogonality relation is as follows. If you take phi I and phi j, now this is equal to the delta ij to pi over 2. Okay, and these are all the same pi, and the only difference is if phi is equal to, if I and j is equal to both is equal to 0, in which case we get the pi. Okay, very nice. So you see how much we gain by not imposing orthogonality, but allowing a weighting function. Okay, so if we allow a weighting function now, we can very easily generate a lot of bunch of other orthogonal polynomials, right? So it's very, very useful. Another one that you can use is a trigonometric relationship. So you can say the 5k is equal to the cosine of phi, right? And this is equal to cosine of k phi. So if you do the math, you will see that these are also orthogonal these are also the good choice of nodes, right? So the roots of this are the Chebyshev nodes. So the xi are equal to the cosine of 2i minus 1 divided by 2k multiplied by pi, okay? Which have a simple geometric interpolation, which is the projection of the uniformly points over the unit circle, okay? This gives rise to the Chebyshev Gauss weights, which are the pi over k, okay? So now the omega i's are pi over k. And yeah, and if you do the interpolation using this, then there is the Runge phenomena is less pronounced. Consider now the Hilbert space L2 of omega, which is the space of all integrable function in which, when we take the inner product and we have this weighting function omega x, then this is less than infinity. Then the Legendre polynomial form a complete orthogonal basis L2 of omega for f of x, which is equal to the summation of this, f of I is equal to this, and the least square approximation f is the spectral approximation, which is obtained by truncating the infinite series. Okay, so here is where we're going a little bit crazy, right? Because before we said we have a finite number of nodes and we have a finite number of functions, m and n. What we can do is that we can say, well, forget about finite. Why are we here struggling to do finite things? Let's just say that you give me an infinite amount of polynomials, and then I can approximate any function on x, okay? So not evaluated on the nodes, but evaluated on the minus 1 plus 1 integral as an approximation of these polynomials. And this is this is how the story goes, right? So the correct way to do this is to define this Hilbert space. So it's a space which is equipped with an inner product and over the L2 square, right? So we take square integrable function with the weighting function omega, and we say, well, we look at all possible functions that we can integrate with this integral, and this omega x is our, it's the weighting function that we have introduced before. And we say that we are happy to consider in this space all the functions that has a finite integral under this weighting, finite square integral under this weighting. And then we say, well, if we take all these functions and satisfy this, and I allow myself to have an infinite basis, okay, then I can approximate any function, right, as this object, right? Basically, I take the evaluation of the function at I, for I that goes between 0 and infinity, and I multiply by the basis phi I. And this is where we have countably many functions. And the weighting of the function is this inner product, right? Is the f times phi I divided phi I times phi I. So the phi I times phi I makes emerge the omega term that we saw before, the omega I term that we saw before. And then if we want to have the best approximation, right, of the function in terms of L2 norm, this will be this infinite series truncated at the M function. Okay, this is where we want to get today. So now, let's try to look at this with some eyes that go beyond the math, right? So what we're saying is this. We are taking all possible functions that satisfy this. And you can ask yourself, what is the order of infinity of these many functions, right? So these functions here, they're all function of x. So in a sense, we imagine that the order of infinity of this set is the order of continuity, right? Of the continuous, right? Is the order of infinity of, let's say, r to the power of something, right? So we imagine that the amount of functions that we can put in here, there are continuously many. Okay. So this seems to be there is a lot of infinity here, right? So there is a lot of freedom that we have in order this. But the beauty of the theorem is telling you this, that any function here that has this order of infinity that you imagine, okay, can actually be approximated with which order of infinity? The countable, right? Because here you have countable many functions, okay? So here you take this function here that are continuous, okay, and you have, but you have countably many of that. Okay, so the order of this, in a sense, it's n, and the order of this, in a sense, it's r, right? So these theorems are so beautiful, right? Because when you imagine this set, you say, oh, this must be as infinity as r. Again, high-level perspective, right? So the infinity that we have in here must be r. So it must be. So if I want to, let's say, explore this space, or if I want to represent this space, if I want to, manipulate this space, then it's so hard to manipulate this space because there are so many elements. And then the theorem comes in. It tells you, wait. Actually, no, right? Because if you choose things carefully, the countability, then you realize that the infinity of this space is only the infinity of this object, right? It's only the infinity of the countable. Okay, so it's, in a sense, the beauty that I see in this is this one, right? You think that you have a space which is very hard to navigate because the order of infinity is very high, and the guy comes in and tells, well, if you choose the basis function in a way which is meaningful, right, so that they are an orthogonal basis, then with countably many infinity, you can represent this space. Okay, this is how I see it. Not only that, the things are even more beautiful than that. And it's telling you that, well, actually, if you just want to take if you want to have an approximation of your function in an L2 sense, right? So you truncate to a polynomial of degree m, and you want the power of the error to be minimum, so the L2 norm of the error to be minimum, then what you do is that you just truncate to the first m order, right? So you drop out the higher order. Very good. So let's discuss a little bit with this, what is the spectral approximation. So the continuous spectral approximation is this object, right? So you take the summation of the polynomial, and you take the first m terms, and you say, well, the function is here, right? And you can also do a discrete version, so you just evaluate over the m points, and it's here. And you see that if you approximate the dot product with the discrete weighted products, then this is your approximation. And you see that the discrete, the Gauss-Legendre interpolation is a discrete spectral approximation of this object, right? So here we take the function to be continuous function. Here we evaluate it over the nodes, and we get that this is good. So using the spectral representation has many advantages for functional approximation. This is more stable, converges rapidly, and you can always add more basis function very easily. The convergence is sufficiently smooth, meaning that if you look at the way in which the error scale with a certain dimension d, this is very powerful. And there is this n to the d, so that scales faster than the power law, so it's faster than a polynomial. This is called the Sobolev form of the function, not relevant for you guys. And this is called spectral accuracy. Then we do some nice numerical interpolation, so you see how much the approximation improves using the Gauss-Lagrange interpolation. We don't have this many peaks, and these are the interpolation error of the global polynomials. This is the local polynomial interpolation error, just nice pictures. And I think we finish here today in the 30 minutes that the students gave me to present. So we start by defining a dot product. Once we have a dot product, we can define orthogonal basis. Now, once we have the orthogonal basis, we can define some polynomials that are orthogonal on -1 + 1, knowing that if somebody gives us another function, we can always reconduct it back here. So once we get this on this -1 + 1 interval, we can discretize using the Gaussian nodes, which are the roots of the Gaussian polynomials, and this converts the continuous dot product into a discrete dot product. And you have these three orthogonal bases, right? So the bases are orthogonal only on these nodes. So then we look at the spectral approximation of a function, which is the approximation of a function with a polynomial with a minimum L2 power. And then if we represent a function using these polynomials, then we have a very good spectral convergence of the approximation to a true function. And then if you want to use this tool for larger intervals, you would just use a piecewise spectral approximation. Okay, very good, guys. We stop here. We stop the recording. We say hi to the people over YouTube. Subscribe, click the bell, and see you soon. Okay.